All right, we're going to continue looking at our introduction to logarithms. We're going to look at exponential function, or sorry, not exponential, logarithmic functions. An introduction to them. Now we're not going to get too complicated. We're just going to kind of touch the surface of them. This is an introduction. There's much more complicated types of logarithmic functions, but what we're going to look at is working with something in this format. Y equals log some base of x. And so some properties, there's two situations. You could have a base that's bigger than 1 or a base that's between 0 and 1. And in both of those, you're going to have the same kind of features for this graph or these functions. If the base is bigger than 1, your graph is going to look something like this. If your base is between 0 and 1, your graph is going to look something like that. All right. So some features here. They both have x-intercepts at 1, 0. And their domain is 0 to infinity. So just quadrants by default. We can move the function of things, but the default quadrants are 1 and 4. Range all the way from negative infinity to positive infinity. So you can go up and down as far as you want, but you can't go any farther than almost to 0 left. And then the reason why is there is a vertical asymptote at x equals 0. So there's a vertical line right on top of the y-axis that you can approach, but you can't touch. Now, this should sound vaguely familiar. You're like, I think I've heard something like this before. And that's good because it's a connection to the exponential function. So with the exponential function, let's say we had y equals 3 to the x. That looks like this. That graph looks something like this, crossing that 1 on the y-axis. Whereas if you had y equals log 3 of x, that graph would look something like that. Now, if I was a really good artist and really consistent in my drawing here, what I could do is, let's see if I can do that. If I can, I would be able to move this over. You can even see my vertical lines aren't even lined up with each other. But they would form a pattern with each other, and that pattern would be, they would be symmetric relative, if I did a better drawing, to the line y equals x. These are inverse functions of one another. So if you look at all their features, you'll notice like the domain and ranges are flipped around. You have this one has a y-intercept at 0, 1. That one has an x-intercept at 1, 0. So again, the x's and the y's are all flipped around. So if they talk about, look at the exponential function version of it, that's what they're trying to get you to think about, is that it's flipped there. But you can always go back, and say, okay, what does this graph look like? Now, we can have those transformations, just like we have in the past. So if I want to graph y equals log 3 of x plus 1, now you got to be careful. What do I mean by log 3 of x plus 1? Is the x plus 1 inside of the log? And the answer is no, it's not. So this change is 1 unit up. That's that type of transformation. So when you add a number on the end of the log, you're moving 1 unit up. So this graph, I would draw my normal log 3 of x graph, but I would move it up 1. Now, if I wanted to graph y equals log 3 of x plus 1. So see, I'm putting those parentheses there. That type of transformation is 1 unit. And again, remember, when it's in the inside, it seems kind of backwards. 1 unit left. So I would draw my log graph now. 1 unit left. And now I would have a vertical asymptote here at -1. All right. So all those transformations still apply. If you put a negative inside with the x, that's a sideways flip. So now your graph is going, it's reflected relative to the y-axis. It's flipped sideways. If you put a negative on the outside, that's a vertical flip. And so now my log, and it looks like that other function where the base is smaller. And there are ways to convert that function into that with a 1/3 exponent, but, or sorry, 1/3 base. But, you know, it flips it. It's how I'd like you to think about that with those transformations. Okay. This brings us a little bit of looking at this. You know, if I looked at this function or this function, their domains would be different. The domain of this function would be bigger than -1. And the domain of this function would be negative infinity up to almost 0, right? So, you know, the domain can change. And so this brings us to the last rule of domain. We talked about domain of functions before. And I said there were 2 rules, but there was another one coming. This is the 3rd one for this course. So just a reminder, the first rule is you can't divide by 0. And that still applies. All these are still going to apply. So if I had a function that looked like this, my domain would be x cannot be the number 3, because 3 minus 3 would make me divide by 0. The second rule we ran into was the inside of an even root must be greater than or equal to 0. And that's because with functions, what you want to do is go from real numbers to real numbers. You put real numbers in, you get real numbers out. And so I don't want to put a real number in there and get an imaginary number or a complex number, a non-real complex number. So that's what this restriction is. So if I had a function like this and I said, hey, 3x minus 4, what I'd want is 3x minus 4 to be greater than or equal to 0. And if I work that all out, I'd find x has to be, for my domain, x has to be greater than or equal to 4/3. Okay, so this is the 3rd rule. The inside of a logarithm must be greater than 0. So not even equal to 0. It's got to be positive. So if I say, you know, let's see, what do we do? X plus 1. So if I say I have h of x equals log 3 of x plus 1, what I would do is I would take that x plus 1, that part inside of the log, set it greater than or equal to 0. So my domain would have to be x is greater than -1. So -1 to infinity, not including -1 because it's not equal to. That's how you figure it. And just like before, you know, you can have more complicated, you know, find the domain. And it's something like f of x equals log 1/2. So it doesn't matter about the base number for this particular thing because the domain, that doesn't affect the domain, just affects whether it's going up or down, you know. So, but let's say we had x squared minus 7x minus 18. Okay. So what I would do is I would take that inside part if I was looking for the domain, and I would say it has to be greater than 0. and then I'd work it out. So this is a nonlinear inequality. You're going to find the critical values. In this case, those critical values are going to be 9 and -2. You're going to draw the number line, label those, and do a sign graph. It can't be either one because this doesn't say or equal to, it just says greater than 0. So I would pick numbers and test them, like -3, 0, 10. Put 0 in there, that'd be -18, -18. That doesn't work. You put 10 in there, that's 100, -70, -18. That's going to be positive. So 100 -88. So that area is going to work. Put -3 in there, that's going to be 9 plus 21 -18. Yeah, that's going to be positive. So that area will work. So my domain is -infinity up to almost -2, union 9, just past 9 to infinity. So it can be complicated, but we've done those problems before. Just set it. The big thing is to know to set it greater than or equal to 0. Or sorry, not greater than or equal, just greater than 0, and work it out. So that's kind of the big thing with that domain. Okay, bonus content here. So on the previous video, there was something I was going to talk about and I forgot, and that is some special logarithms. And there's two special ones. There's the common log. And the common log, this is log base 10. So sometimes you can just write log base 10, that's fine. But a lot of times people won't. What you'll see, or on calculators and things, they'll just say log. So if you ever see a button that says log, what they're talking about is the base you're working with is 10. So that, at least directly, will not calculate like a log base 2, log base 3, log base 27, log base 1/2. It won't do those directly. There's ways to work around it. We'll see that in a coming video. But the normal log button is just log base 10. And so like if I look at this calculator, I have log, that's log base 10. That's what it's talking about. If I said, the way this does is you put the number in first, and then you hit the log button. So if I said, what's 10, log base 10, it should be 1, right? 10 to the first power is 10. So what's 100? Whoops, yeah, let's clear that out. What's 100? 100. What power of 10 gives you 100? Should be 2, right? So that's when you see log on a calculator, that's what you're talking about, base 10. And then we have what we call the natural log. And that is log base E. Okay, so the reason why 10 is a common log is our number system is based on tens. 10 ones make a 10, 10 tens make 100, 10 hundreds make 1,000, so on. And our entire number system based on the number 10 because, right, 10 fingers. That's why we typically, most people have 10 fingers. That's why we base our number system on that. That's why we developed it that way. There's other systems you could do. So that's the common log. Log base E is Euler's number. It's an irrational number. It's oftentimes used to describe natural systems like bacteria groups, viral infections, things like that. So we have a special thing for that. And E might think, hey, why don't you just call me log? I'm special. And 10's over here like, no, I got that. So just keep in mind that a lot of math was developed in non-English speaking countries. And sometimes their adjectives and nouns kind of flip-flop. So this is, instead of saying the natural log, what you do is say log natural, right? The log, the natural log, the log that's natural. So when you see ln, that just means log base E. So on a calculator, you'll oftentimes see that. It'll usually right by the log button, ln, that means it's log base E. So let's see. So if you had ln 3 equals x, what that's saying is e to the x power is 3. That's doing that translation there, that you start with the base, so it's ln, so the base must be e. Your exponent is the next thing, and then your value. So e to the x equals 3. E to the x equals 3. So the base is there. We're just not writing it. All right. And I will see you in a coming video.